Hello community! Should you trust AI benchmarks? Is it really that an AI is working hard here for a benchmark evaluated by another AI and data generated by other AI system? Is this really what tells you what is a good AI model? Or is it completely different? That AI is smiling during here the benchmark test and it knows already all the answers. So how are benchmark deceiving us? Right now, today, what are the latest research publications on this? And talking about it, hey, we have a brand new one, July 16, 2025. And it is from Apple, University of Washington, and Stanford University, and one of those is now at Tropic. So you might say, hey, wait a minute, Apple? You really want to tell us that Apple published a new study? You know, the Apple that had the illusion of AI thinking? Now AI is doing the illusion of AI benchmarking? Are you for real? Absolutely. Apple has here a new study, and it's a beautiful new study. And whatever you say, but they don't have Siri, an intelligence here, you know? They have not even a single AI optimized version that really... Okay, so we are talking here about Apple research on benchmark targeted ranking. So how does your AI model rank better if you do here a benchmark targeted exercise? Let's start. Now, you know the simplest case, you align your pre-training data of your LLM with the content of the benchmark tasks. And you know, Apple says, you know, let's make this transparent. Everybody is doing it. So let's look at it at a scientific way and let's examine here how much compute do we really need if we already have a pre-training data on the benchmark task. So we have here a specialist model, and now let's have a look at the targeting of individual benchmark. And Apple said, you know, this is a kind of a paradox, because why better scores that you see that are published here? No? Global corporation come out and say this new model is the best benchmarking model. It has the highest benchmark score on all benchmark. Why does this mean nothing at all for the AI model itself? So Apple said, hey, you know, we need two distinct set of benchmark for the targeting and the evaluation. And they go with the core benchmark, and they have 10 benchmarks that are really known. And I have given you the reference, so you see, my goodness, they are from 2018, 2013. So those benchmarks are known for years. Those are familiar benchmarks. And then we have non-core benchmark, and Apple goes with 39 benchmark. So, hey, Apple is really trying to show us here this diversity of benchmarking. Of course, there's now a brand new idea with Apple. Apple doesn't go and say, hey, let's benchmark GPT upcoming 5, or let's go with Grok 4. No. Apple says, you know, we do this in a neutral way. We do this in a very diplomatic way. We build our own models, and we have data pools. And the first data pool here is a very specific data pool of 2024, and this contains about 24 trillion tokens. So let's say it's almost the internet. And then they have a second Nemotron CC dataset, and this contains here an addition 6.3 trillion tokens. So they say, you know, this is our basis where we do the pre-training on. And those are available, and this was published, so we know exactly on what Apple is pre-training its own model. So here we have it. This is the study here, language model improve and pre-training data match the target task in the evaluation dataset. What a coincidence. Here you have the archive link, and it's simple asking a question. Hey, what happens when we make this optimization that some AI global corporation do explicit? Let's have a look at this. Let's be honest. Let's say, yeah, maybe some AI models, some large language model are optimized for the performance benchmark that we know that everybody will do this performance. And Apple tells us, hey, now we pre-train their own models here for it's not cheating. No, absolutely. It is an optimized learning. And later it's a hyper-specialized learning of new LLMs for specific benchmarks. Yeah? Please, as a non-English speaking person, I have to be absolutely precise here that you do not get here wrong impression. Now, this pre-training of Apple models is done in a very specific and a very intelligent way. Let's have a look at this. So they say, okay, we take all the benchmark. We know, no? If a new LLM comes out, we know there are 10, 20, 50 benchmarks. So we take all those benchmarks. We have it. It's published, no? Great. And then we have here all the other documents. There's, 20 trillion tokens that we train our models on. But now, since we go with small language model, there's something special. So we have here the benchmark examples, and we built here a vector space. We just embedded here in a mathematical space where the semantic similarity is now here in a location similarity. So whatever embedding model you go, we just embed everything from our benchmark example. And then we embed everything of the trillion tokens. And then what we do, we look here in this mathematical vector space, what is similar here to our benchmark examples. We do not go with exact identical vectors in a 1024-dimensional artificial vector space. No, we say, hey, what are the top 100 vectors that are real close here to this particular benchmark that everybody knows now for 5 years? And then we take those, let's say 100 vectors, and we say, okay, so let's take here the top 1% or top 3%. So we score this on a similarity to the real benchmark data. So we want just the training data that are absolutely close to the benchmark data. And then those 100 surrounding vectors, we do re-embedding, and then we have here the training data for us. And then we just start here with the training, and we have a pre-training. We don't go with reinforced learning, no. Real pre-training, real beauty, real powerful pre-training. Gorgeous idea. I like what Apple does here. And I thought, but wait, how close are those vectors to the original vector that is really the benchmark itself? Yeah? And Apple thought about this, and here we have it. So here we have the top 0, top 10, top 100, and here we have the similarity to the matched one. So Apple says, hey, we are careful, no? Exclusively uses here the official training set of the benchmark, but we do not learn the model on the test set that are really the real test. No? We just go with the training set of those benchmark. And just to be clear here, kept completely separate here, never used it at the real test set in the data selection process. And they say, Apple tells us, hey, this is a fundamental rule to be here fair and open and have a fair evaluation, because otherwise we would just train here our new LLM on the real benchmark data and with real answers. And I mean, come on, yeah, then what we do this evaluation for, no? So we are fair, we have ethical standards, and we just go with the data that are real close in the vector space. But how close are they? No? Now, they run this here and they say, okay, look, if we go here at a certain percentile, we are here between 60% close to 80% close. Or if you want, 1.0 here is the perfect overlap of the cosine similarity, no? And we go with 0.8 to 0.6, and we take here the top, 2-3%. So these are really close here to the benchmark data, but not that close. And you see, if you go then with 30%, you would have here a cosine similarity of 0.4. So this means you would have a lot of data that are in the right domain of your benchmark data, in the right, let's say, structure, how you question this with a question and answer, in the right format, in the right logic, in the right specialization, but not absolutely. So this is now absolutely fascinating. And then Apple tells us, it could be that on the internet there are those benchmark with solution. So we don't want this. We want to have clean data. So we even have then a scan for matching here n-grams of the real benchmark, and we don't want them in our training data set. And here I think this is just an example that I have, for example, in the benchmark data, in a trivia question and answer benchmark, you have a very specific format. Question, which band wrote the song Stairway to Heaven? And now in the web data, in this 20 trillion data, there's this now. And you see, it is different. It is not a cosine similarity of 1, that this is really the identical question, But now let's say in the training data on the web, you see, hey, Led Zeppelin's fourth album, a masterpiece of rock, featured here their legendary anthem, Stairway to Heaven. So you see, if we take now this string of token and we do here an embedding in the mathematical space, look at all the different words that we have. Fourth album, a masterpiece, rock, featured, a legendary anthem. So of course it is not really the identical vector in a 1024-dimensional mathematical vector space, because if we build this vector, and let's say we just concatenate it, or we take some specific average, no? Look at all the different words we have. So if we look back here, yeah, 0.6, 0.7, 0.8, this is absolutely, but you see, we do have here the answer in our training data set for the pre-training of the LLM that Apple did. So it's not even close to a cosine similarity of 1, but you understand what Apple said? That, listen, I don't want to go here with the real answer. I just want to be just in the epsilon environment of the correct answer. And then something really interesting. Apple said, hey, can I manage to do or find some new scaling laws, deduct new scaling laws? So this means, can I create a new mathematical formula that can predict if I have a particular LLM, can I predict the performance of this LLM at a particular scale? And interestingly, they found a new law. But let's start at the beginning. So what we have here is Apple said, okay, listen, I do now a pre-training of 10 LLMs. And I have here all my benchmark. Here, you see here the columns here with the benchmarks. And then I do here, I pre-train an LLM on this specific target. So you see, you have RC easy. So whenever we're in the diagonal here of this matrix here, this is exactly this test where the LLM has been trained on this test. And here in bold, you see what a coincidence. If the LLM has been particularly trained for this particular test, you have the best performance data. So you see, we have here bold in the diagonal. And then Apple tells us, hey, what a coincidence, no? Yeah, but look at the other performance data, no? If we go for MMLU, you see the other 9 LLMs that were trained on different benchmarks. 53 is the best one, no? MLLU, but the others have only 26%, 28%, 48%, 47%, 42%. So you see, in the other benchmarks, if you just train it on one benchmark, the performance is diminishing. And this is one of the main lessons that we know, but Apple kind of confirms here for us. Eh? But Apple said, hey, for finding these scaling laws, I have to have a lot of models. Eh? So Apple said here, okay, so I take now here for this scaling law, only for this, I take 11 different data sets in total. And for each of these 11 data sets, I have to build models. No? And I build now LLMs, and I build an LLM from a size of 50 million free trainable parameters up to 6.6 billion trainable parameters. So for 8 different model sizes. And then for each of those model sizes, I have 8 different training token counts on the amount of data that I do my pre-training, from only 1.1 billion tokens up to 152 billion tokens. And I do this on all 11 data sets. So you see, if we do this for each and every, you have more than 500 models that Apple trained here, pre-trained here on very specific benchmark data sets. Now you might say, yeah, and the rest, there's not a lot of rest, because this is just here if you want an experiment that is done. Hey, listen, if I have, 500 models and each was trained on a particular benchmark, what is now a law that I can find with AI? Now, we don't need AI, because if you plot it, you see it's just here a linear correlation or a power correlation or maybe a polynomial correlation. So let's have a look at this. What did Apple find? Our representation on the x-axis on a 3-dimensional model, we have the model size. So the number of parameters, no? 50 million to 6.6 billion, and I think 6 billion to 7 billion LLM. This is a model size that we use even at home. Now, this is something you can have in a 4-bit quantization on your PC at home. On the y-axis, you have the training data, the number of tokens here that were used here for the pre-training. On the z-axis here of the model quality, you have now the loss. If you calculate the loss function, what is the minimum loss you achieve with one of your 500 models? So you have a huge data set. No? So let's look at this. This is a three-dimensional representation. We just talked about the training tokens, the model size, and the loss. And you say, okay, this is an interesting distribution on a hyperplane. But then you go on, because in order to find here a scaling law, you have now to create here kind of a translator, no? That converts here the abstract pre-training loss, the specific loss here from step 1, into some benchmark accuracy parameter. And there, so specific benchmark, trivia, Q&A, take all the models they train in step 1 and plot here their final accuracy against the loss and fit it over a sigmoid function. And then you get this. So you have now accuracy against the loss. And then you're saying, I would like to combine this. And this is now what Apple did. It was not satisfied with the accuracy. Yes, of course, if you trained a new LLM only on data that are absolutely optimized for one specific benchmark, guess what? You have a great benchmark score. But Apple said, I want to go a step further. I want to see about the compute in flops. What is it? How long do I have to compute this? How good is the model? How less time, how less energy do I have to use? So the third step was then simply combine into the accuracy scaling laws, the benchmark here, put it all together and create here the final most useful relation between the accuracy of the model and the compute in flops. And then you see this here. And then we're almost there, because now the fourth step is simple, comparing here the training data set, using here the scaling fits here, and the goal is here to compare the different data selection methodologies against the baseline. And now you see it. No? If you have here a horizontal line at accuracy, let's say 50 or 60%, now you see the differences. So what we have now, if you want the horizontal gap now between the two curves here in our, if you want, step 4, gives us now at a particular accuracy that you want to achieve, that is your goal, 60, 70, 80, 90%. And now this horizontal gap is kind of your compute multiplier. So you have now a direct quantitative measure of how much more efficient one data set is than the other if it has been trained particular for this benchmark. This is nothing special or unique, but we want to know the law and we want to get a feeling on the multiplier. So we are not amazed that it is possible. We just want to get, hey, is it 10%, 100%, 200%? What is it? And Apple shows us here beautifully that the accuracy of the model is only half of the story. And the other half of the story is, of course, how long do we have to compute? Do we have to use 100 GPUs or 1000 GPUs for the task? So you see, we have here this efficiency against accuracy that Apple is examining here for the pre-training of models that are optimized for benchmarks. So let's take the simplest example. We have a baseline model. No? You as a company, you are Google or you are Meta, whatever, you spend 2 million now on pre-training a new model. And this is equivalent that you go with 2 times 10 to the power of 22 flops. And you say, I want to achieve a 70% accuracy on one particular test that I select now before I even start to train the model. Now, with the method B, what Apple said, you can spend only 1 million, half the amount of the money. And you get also a model with 70% accuracy if you do an intelligent filtering of your pre-training data. And you might say, yes, of course, it's logic. If I have here from a complete training data set, I filter out the most efficient training data for a particular benchmark and I train the model on those because I know this will be the benchmark the model will be open to. Yeah, of course. Then I will also achieve 70% accuracy. If I know exactly how or for what I built my model. Yeah? Now, surprise, surprise, model B is better. It achieves the same result for half of the cost. So you see, this is now where Apple says, hey, I want to have now this relation of flops for the efficiency and the accuracy. And this is now interesting. Eh? So Apple is not only that it tells us, well, there are a lot of tricks how you can hyper optimize your benchmark performance, because you know what are the benchmarks your new model will encounter. But let's have a look here at the computational work that the model has to do. If you have it better trained, if it has a better parametric knowledge already, you don't need to compute it as long, because it already has kind of an answer. Maybe it knows the plan how to find a solution. So you see, you can really improve here the efficiency, a leap forward. So the main message of the PDF, if you read it, and maybe I was also guilty of this, I thought, hey, Apple just wants to tell us how to cheat here on the benchmarks. And guess what? Yes, there are a lot of methods how you can cheat with benchmarks. No question about this. And Apple tells us no question about this. But this is not about it. Apple tells us, hey, it is not how you cheat on, if you do the pre-training of a new model, on your benchmark performance. Apple tells us, if you do this, yes, you will get a better score. You will outperform all the other LLMs on the market today. But Apple tells us you will have fooled yourself into thinking you have a better model, because the benchmark will cease to be a reliable measure for the general capability of your new LLM. You just trained it for 10, 15, 20 benchmarks that you know will come up. But this tells nothing about the general capability, about the world models, and so on. So nice, no? And Apple goes on and says, yeah, we know this, no? If you have a specific domain training, you want to have an LLM on medical data or coding, no? Yes, you create here not the super general capability, but you want here a domain specialist for the real-world application in code or medical, no? So the general leaderboards will not be a relevance for you, but you look then for medical benchmark. And they say, hey, kind of warns you about the consequences of aiming your pre-training optimization of your new LLM if you aim at the wrong target or the wrong marketing effective benchmark data. Let me show you this example. This is here, for example, I noticed this is here artificialanalysis.ai, and they have an intelligence index. No? So we know, and this is now for years, if we go there and they have this index, their index is simply 7 known benchmarks. This. So we have 7 evaluation. I know today, if tomorrow I train and bring out a new LLM, I know exactly today I can calculate what is my score. And I can optimize into pre-training my model to achieve here. If you tell me, hey, I want to have an 81%, I can build you an LLM with 81% performance index on this intelligent index, because I know exactly against what am I evaluated, so I can optimize my pre-training data. So what is the value of this? Good question, eh? Explicit data task alignment is an interesting topic. Maybe do not believe all the marketing material by the global AI corporations. So what is here the final and kind of synthesized message here? Look, this is here a beautiful visualization, but it took until now that I can explain what is the content of this. Because, okay, on the x-axis we have flops, the compute. And on the y-axis here, we have here the average of core, that is here the sum here of 10 specific benchmarks. No? And this is here the performance, 60%, 70%, great. So if I go now with a specific data pool that I showed you, this is data pool number 1 from the beginning of the video, you can now say more or less, okay, let's go here with 60%, no? And if I want to achieve a 60% accuracy, so I take here this, I just move over the horizontal line till I hit here my target core. And this here I know, I need here this amount of compute. But I can go on with the 60%, no? Over to the, let's say, the baseline. This is in yellow. So you see, oh, this takes quite a long time. And then I need much more compute if I would go with a baseline optimization. So if you know what you're pre-training your LLM, for what benchmark, for what performance, in what domain, for what configuration, for what data format, for what structure, what information-specific complexity do you want to solve, you can here now, with this beautiful line, get an idea for this specific set on the computation. And here Apple tells us, hey, we found here for this data pool that we have a 2 times compute multiplier. So this means you can effectively halve the compute time for the pre-training of your new model. So you halve the cost, or you halve the hardware resources to reach your target performance. And let's say our target performance was here on this benchmark test, 60%. So the process of aligning now the pre-training data in the format, in the structure, in the complexity, in the density with the target task, why you build an LLM, is now an incredible powerful tool for improving your efficiency and controlling the capabilities. But if you would, now let's say theoretically, I would be a CEO of a global company and I would say, hey, I bring out a new model and I want that in 8 benchmarks, this model is the best benchmark score of today. Yeah, you can build this model rather easily, but it doesn't tell you anything about the real world performance for your data in your domain because it was optimized here for benchmarks. So Apple tells us, hey, if you do this only for benchmark optimization, you devalue here the benchmark idea itself. Apple has another insight that is interesting, and this is here. So we have the core versus the non-core performance. So here we have the core performance, let's say in percent, and the non-core performance also. And now there is an interesting law. I was not familiar with this, and Apple tells us, Goodarts Law. It runs the following: when a measure becomes a target, it ceases to be a good measure. What does it mean? It is more or less an empirical proof that you can fool yourself, and this is really shocking. No? So this is, Apple says here, the first large-scale empirical proof that this law is in fact true for the action on the LLM pre-training. And the rank reversals, where the best model on the target benchmark becomes one of the worst models on the held-out task. And you have it here. If you go for the core task here, and we go here with the target core, and we have optimized this for the core, yeah, we have here, if you compare this to the other models here, outstanding. This is the best performance, 66.5. But if we take the same model and go now to a non-core task, to different task, you see now that the other models now get better and better because maybe sometimes they have been partially trained on this pre-training data. But this model that was the best suddenly becomes now the worst model in the bunch if you go to out of domain data, out of distribution, and whatever. So however you specialize your model for one particular task, for one particular benchmark, for one particular defined structure or complexity, be prepared in anything else it can crush down and diminish its performance. So this is a kind of a powerful illusion that we have progress here in the AI training and AI benchmarking. Well, actually, we build or create a model that is less capable in general for generalization. So either you can go, okay, and say, I'm fine if I have only specialist model that I can only use for 1 or 2 tasks only, max. And in all the other things, it's just a horrible model. So you design your own model for your specific task. But generalistic models like OpenAI is trying to do with O3, or Grok with Grok 4, they have now a real different life. But they have one fact that helps them. Let's talk about this. Here, ARC price, you remember here ARC AGI 1. And this here is for AGI 1, the current performance you see here. And this indicator here, this little blue dot here is OpenAI 04 mini high. And this is impressive in its performance. It is close to 60%. This is where 03 high is. And here 03 Pro is. And Grok 4 in the max syncing mode has now 66%. So if you think that this is kind of a free model by OpenAI, if you just give your email to OpenAI, you don't have to pay the $20 for this, and you have to pay for Grok 4 thinking, the free model and the best other model, they're not so far apart, which is simply amazing, no? But of course, it goes on. And just days ago, we have now the AGI 3, complete new benchmark, a reasoning benchmark for the next generation of AI models. In my last video, I talked in detail what is the background of AGI 3. Now you can do it. It is available in an early beta for you, for everybody, and they give you a beautiful explanation. But if you've seen my last video, you know everything about it. And the main idea is that with ARC AGI 3, you have now a diverse benchmark targeting that fosters here broadly useful capabilities rather than absolute specialist with narrow task-specific behavior. No? So you want to have a model that is a generalist, and this is here the perfect future benchmark coming up. And if you've seen my last video, you know exactly what is the background world models within the LLMs. So yes, if you look back at this new publication by Apple, it is kind of a transparent cheat code. Apple tells us, yes, you can optimize each and every LLM for a particular benchmark. Of course, you know it. But in a sense that you are hyper-optimizing here for this test. And if your only goal is to get you the highest possible score for the marketing material, okay, but be aware that you have then a specialist that is not a generalist. But yeah, this is the most effective way to do it. So if you want the hyper-optimization for your known benchmark that you can anticipate your LLM will be tested against. And Apple tells us, hey, the paper's main message is not to do this blindly, but just to say, hey, can you trust benchmark at all if the developer or the global corporation or the CEO knows he will get a $10 million bonus if I don't know what happens? And the authors use this incredible efficiency gain now for a deeper scientific point. Yeah? They say when this happens now, the model becomes now a narrow specialist and performs poorly on all the other laws. And the scaling law is now the only thing left. So let's have a look at this. But in general, you can say the insight is smaller models, no, like a 6, 7, 8 billion pre-trainable parameter model have limited capacity and benefit most from a very high signal-to-noise ratio. So you need some aggressive filtering, especially if you are at a 1 billion model. But if you have larger model sizes that have the capacity in the neural network complexity to learn from a more diverse and noisier data, then this diversity ultimately allows this bigger model, bigger LLM, to achieve a better performance at scale. Is it new? No, not really, but now we have the data to back it up. So what is this scaling law? I give you here the result. You find a lot of data here in the report. You have own annex here, I think 10, 20 pages, where you have detailed data. I give you the result here. This is it. So we have the flops here to the filtering rate, to the optimal filtering rate, to the top percentage that you need to have the best performance for your specific model size with your given limited budget for compute in flops. So if you have now, and this is it, this is here the line, this is here the mathematical formula if you want. So if you have a low compute budget, let's say you're a small little laboratory or you're at a university and you have this budget here. So the law predicts now your optimal filtering rate, and it tells you, hey, you have to have a real aggressive filtering rate. And at this scale and at this flop, the top 3% filter gives you the best performance for your LLM. So what you need a very high quality signal-rich data, the best 2-3% here of the complete data you have available, because your model is so small and your model cannot handle much noise. So you have to have the perfect data, absolute low noise ratio, and then you will have a good performance. But of course, there is a saturation. Now, and they say, hey, if you have a high compute budget, let's say you have 1,000 times more compute budget available than this low computer, this law predicts now you should filter much less because your model is able to run on the diversity. What your filter should now be, it should be a top 30% filter. This is your optimal filter configuration. Think about it. Because your massive model has now the capacity to benefit from a much wider variety of data. This new data diversity from format, structure, complexity allows now the LLM to achieve a higher performance than it would with this narrowly filtered dataset. This is now an interesting relation, and for the first time for 500 models that Apple did here, and of course transformer models, we have now a law for this. So what is the main point? If you have a high compute budget, you would go with a filter rate and you would say, I only take the top 3%, so the best training data. This would be a mistake because your performance would be limited. But if you have a high compute budget and a, let's say, moderate model size, your filter rate can be 30%. You can take a lot higher diversity of your training data for the pre-training. You don't have to focus only on absolutely narrow positions, vector positions in the mathematical vector space to the benchmark data, because your model can learn from a lot of other vectors that don't have to be as close as if you would have a low compute budget. And you see, if you have a filter of 30%, you achieve an accuracy or a performance of 70%, the best performance. So the more powerful model has the capacity to use here more diverse data to reach its full potential. And this is the optimal setup. So if you have a huge model, don't filter to the extreme. Don't only take the best result, the most correct results. You would reduce your overall performance. And it's beautifully shown here by Apple in the paper with a lot of additional data. So if you go run on a high compute budget, if you have enough GPU, if you have the time, you leave performance on the table if you're being too strict with your data filtering. You need here to match here the data diversity to the model capacity. And exactly this ratio is this power law this scaling law that we found, that Apple found here for this configuration. So if you want summary, small LLMs, especially so 1 billion models, now need data purity to have a good benchmark performance if you train them on those data. And large models need a data diversity to learn not only here the benchmark data complexity, but a little bit to the left, a little bit more to the right, and maybe up and down and all around, much more diverse data, a better understanding general on the complete domain. Interesting. And Apple here, if you have it a little bit on a meta level, advocates here for a compute optimal scaling. So this means if you increase now your total compute budget, you should simultaneously increase both your model size, go from a 7B model to a 14B model, and the training data, the amount of training data of your domain-specific pre-training that you give to your model for the pre-training. Increase this model size, increase the amount of training data, and more of the compute budget gives you here the optimized sweet spot of the performance of your new LLM. Absolutely beautiful. So you see, Apple kind of provided here absolute fascinating insight and answered the question, hey, are those AI benchmarks deceiving us? I hope you enjoyed it. If you want, subscribe, and I see you in my next video.